Hello everyone, my name is Chengyao. Today I'm going to present our paper, Accelerating TE-based DNN Inference using Mean-Shift Network Pruning. This is a joint work with my colleague Shangqi at Monash University. Machine learning is used everywhere these days and always led to the breakthrough in a lot of areas in the internet for image recognition, speech recognition, and natural language processing. Because it is very useful and for its wide application, it has been provided as a cloud service. In such service, the service provider usually requires user to upload the inference data to the cloud and return the prediction result to the user. However, the use of such cloud service raises privacy concern. For example, some datasets are high-valued assets for the enterprise and should not be revealed to the cloud providers. So how do we solve this problem? Privacy-preserving machine learning provides a solution for this security concern. It enables a service to still perform the same machine learning algorithm without knowing the underlying content of the user's data. So in this way, we can still gain the benefit of the service while protecting our data privacy without leaking the information to the service provider. And it is also a very active area of research. Existing studies in this area can be classified into software-based solution and hardware-based solution. The software-based solutions leverage the cryptographic tools like homographic encryption and secure multi-party computation. Those works achieve a high level of privacy protection. However, due to the nature of cryptographic tools, those approaches introduce a large number of computation operations. Thus, they are hard to deploy to protect the complex DNN models without incurring a significant inference latency. And hardware-based solution, also called TE-based solution, relies on the trust hardware to process sensitive information within an isolated environment, which is also known as an enclave. It has been widely used in many application contexts, such as encrypted database, secure network functions, and also become a promising alternative way for the cryptographic tools when designing privacy-preserving machine learning algorithms. Nevertheless, the existing works demonstrate that the limited memory size of the enclave restricted the performance of the DNN inference. To elevate the memory consumption and accelerate TE-based DNN inference, we present a novel network pruning algorithm based on the mean-shift clustering technique. We implement our algorithm and use it to prune three most commonly used DNN models: ResNet, DenseNet, and VGGNet, which is trained with a certain dataset. Then, we conduct the inference task over our compressed DNN models inside the Intel SGX runtime called Oculum. Our experimental results show that the proposed algorithm can effectively recognize and remove more than 35% of redundant parameters for all the three networks, together with an approximately 30% reduction in the floppers. Moreover, compared to the on-prem network, the inference delay of our prime network is reduced by 20% under the Intel SGX environment, and it only introduces a negligible accuracy loss, which is only 0.1%. To accelerate the DNN inference in the enclave, we design a network pruning algorithm to remove the redundant part of the DNN model. During network training, parameters update will cause input data distribution in each layer to change continuously. Whenever the parameters are updated in the upper layer, it will eventually cause a change in the input data distribution in the lower layer. This creates a completed data distribution which makes the analysis of the relationship of the weight data a difficult task. In deep neural network, this phenomenon is more serious. The batch normal algorithm normalizes the input at each layer to make the input data distribute stably during the training process to solve the above issues, which will also reduce the difficulty for analyzing the relationship of the weights. After selecting the batch normal layer, we choose to apply the mean-shift clustering algorithm to clustering the weight value of the batch normal layer and perm out the unnecessary channel based on the cluster. The mean-shift algorithm is a clustering algorithm based on the cluster center, like k-means, but the difference is that the mean-shift algorithm does not require any prior knowledge about the categories. Specifically, the mean-shift algorithm employs an iterative steps in which the offset mean of the current point is calculated. The point is moved to the offset mean, and then this is used as a new starting point to continually move until the final condition is satisfied. In this work, the input data set in the weight data is the weight data of each batch normal layers, and the radius is automatically detected by the built-in function. After getting the result on the clustering, the information is passed on to the channel perming process. In the above steps, our approach generates the mean-shift clusters. Next, it selects the permed channel by using the minimum value among all cluster centers. The weight value smaller than the minimum cluster center's value will be permed out. In the perming phase, our approach will perm the channel by removing all their incoming and outgoing connections and the corresponding weights. The purpose of using perming is to make the deep neural network into a relatively shallow network, and the advantages are undeniable. By using the channel-wise perming, the permed network does not require any unique toolkit for the inference acceleration, which means it can use in any platform without requiring any extra hardware acceleration method. To evaluate our work, we use the following experiment setting. We evaluate our work upon a certain dataset, which is a small dataset for identifying common objects containing 10 categories of color images. We use 3 well-known CNN models to evaluate our design, which are VGG16, ResNet 164, and DenseNet 40. We use the Google Cloud Virtual Instance as a platform to test our design. For Intel SGX runtime, we choose to use the Oculum. The Oculum is a multiprocessor library OS for Intel SGX. It provides a container-like, user-friendly interface that allows the application to run on the SGX with little or no source code modification. Due to the limitation of Google platform, we use the SGX mode in the simulation mode. Here let's see the experiment result. In our work, we aim to reduce the number of computational resources required for the DNN inference. From this figure, we can see that each model has over 35% of unnecessary channels permed out. For VGGNet, we can find that over 50% of redundant parameters can be permed, while for the ResNet and DenseNet, the perm ratio on the parameters is relatively small, just around 34%. After analyzing, we believe that this is because those two networks are more compacted than the VGGNet, and the structures in those models already provide some channel selection functions. Let's move to the inference latency part. We compare our work with two baselines. The first one is SGX, which means runs the model inference in the enclave, but does not perm the model. We use this baseline to show the effectiveness of our approach in reducing the wait time for model inference in the enclave. In the second baseline, which is a native, it means that the model inference is running as a general program without the protection of the SGX. We use this baseline to investigate the overhead of our work. We can see that DNN Inference has a significant latency in the SGX environment and up to 9 times in the VGGNet inference. In this figure, we can see that the inference speed of the perm model running on the SGX is significantly improved. For the VGG16 the inference speed is improved by 37% compared to the unpermed model. On the other hand, the speed of the ResNet and DensNet were minor, but also improved about 20% for each. This figure also compares the inference speed of the unpermed model running in the native operating environment with the permed model running in the SGX enclave. Although our solution incurs an extra inference latency, it is still a significant improvement compared to the directly port the inference service into SGX. Now let's move to the discussion part. The first point is that the perming rate. We choose to use the minimum point in the cluster result as a perming standard in our experiment. This figure shows the weight distribution after the mean shift clustering. In order to improve the perming rate further, we have considered using the mean value of the all clusters centered as a perming standard. However, we can see from the figure that most weight distributions are below the average, leading to a significant perming rate. On VGGNet, we use the average value for the perming, which into some layers has been completely permed, thus destroy the entire network structures. In ResNet and DensNet, we can achieve a high perming rate by using the average value. However, due to the fine-tuning process, the model's accuracy is greatly affected due to the reduction of the channels. To sum up, we can say that mean-shift clustering helps us to classify the weight value effectively, but it is challenging for us to filter out more irrelevant weights from the cluster class and increase the perming rate. To sum up, this paper presents an unsupervised clustering perming algorithm based on the mean-shift clustering, which can effectively compress the existing DNN models. Our evaluations over certain datasets with 3 models shows that our permed algorithm can reduce flippers and parameters by more than 30%. After deploying the permed model to SGX, our method speed up about 20% compared to the traditional DNN inference service in SGX. The proposed algorithm enables a completed DNN models to fit into a constraints of memories under the SGX environment. Furthermore, it successfully reduced the inference latency in the SGX while preserving the privacy of users' data and the model. We also point out our future direction of our work. The first one is using GPU acceleration. Using GPU acceleration is currently the mainstream acceleration approach for DNN models. Nonetheless, the traditional SGX does not support the use of GPU. There are some work tried to use GPU in SGX, but they still have some limitations. And another direction is using convolutional computation acceleration method on the permed model, which can save more computational resources. That is all for today's talk. Thank you for the listening.